So in this tutorial, we're going to be going through a really short beginner for M4 and parallel programming. So M4, the traveling courier problem. You're given a bunch of depots, you're given a bunch of pickups, you're given a bunch of drop-offs. You have to pick up every pickup, then drop off every package you picked up. For every package, you have to first pick it up, then drop it off, but you can reorder the packages in any ways. You have to find the fastest delivery route. How to do that? This is actually a research problem. It's NP hard, so there's no way that you can find the optimal solution. You can just optimize your algorithms to find a better one. How to do that? The general structure, first you'll have to estimate the travel time between all of the locations so you can have something to start with. And as usual, this happens in preloading so that you can access them in all one time after you store everything. And then you have to find a good delivery ordering and then return the final tour. For all of these, in this tutorial, we'll be covering the first one. The second one, your lecture should be covering a bunch of ideas. And also the third one. So we're going to be focusing on the first one, estimate travel time between all of the locations as a pre-compute. All of these should happen in less than 50 seconds. And that's why it's really important to do the pre-compute. We want to pre-compute for each of the intersections that we're interested in. And that means the depots. We want to make a 2D array or matrix that stores the travel time between from intersection to every two intersection. The option one that is really fast but inaccurate is to just calculate the Euclidean distance using square root of squared plus squared, x squared, y squared. That's inaccurate. So the better option is to use the exact path. It's slow, which is why we'll need pre-compute. So the naive way to do this is we just go all of the source intersections, all of the destination intersections, and we find the A-star path from your milestone 3. What is the complexity for this? Let's say we have k depots, so we have k intersections in here, and v total intersections in the map. O of k times v. How many k's are we looking at?
Okay.
It's a nested for loop of k times k squared, and times the complexity of find path A star. What is the complexity for A star and Dijkstra? You'll be asked this question most likely in LP2. The complexity for Dijkstra and A star is V log V. So the total complexity is then k times V log V. Since we have a k squared, this is going to be really slow. On large test cases, k larger than 300 intersections, it's going to be really, really slow. So we use an improved algorithm. So instead of doing A stars from all of the source to destination, we do multi-target Dijkstra. So Dijkstra, not A star, Dijkstra, in theory, finding the path from the source to all of the target is equal to the time of finding the time from source to one target. If you don't know Dijkstra, I can go over it afterwards. But just take this for granted. Finding the path from source to all of the destinations is the same as finding the path from source to one destination. So we can then turn this, finding the path to each of the destination from the same source, into multi-target extra. And the same complexity. So what is the total complexity in this case then? KV log V. We got rid of one of the case. And this is as good as we can get if we want to store the exact path. What if we want even more speed? We need to start considering parallel programming. Because computing from different sources to all of the destinations can happen in parallel because they're not dependent on each other. So parallel programming. This is usually the same graph that we'll be showing when we want to motivate parallel programming. So the first line is the transistors on chip every year. By Moore's law, the number of transistors on chip grows each year, and this is still true till now. And Moore is one of the founders of Intel. Moore's law. The single-threaded performance, the yellow line, you can see there is a decrease after it gets to a peak point, and then so this is not scaling as good as the number of transistors. And why is that? That's because we want to scale our total power so it doesn't exceed too much. And we cannot improve the max clock frequency on chip anymore after we reach one's threshold. So that limits together the single-threaded performance of your programs. But after this is 2002, we're starting to considering adding more cores to one processor. So one CPU now contains multiple cores, and each core can do its own job. So we can then multiply this by the number of cores to get our multi-threaded performance up. And that's why we want to take advantage of the multiple cores on your processor. A multi-core processor will look like this. You'll have this example shows 4 cores. You can have more according to your computer, your machine. Each of the core will have a little bit of its own private memory, but the most memory are on the shared memory here. Each core can execute its own instructions independent of each other. All cores share a common memory space. And from the programmer's point of view, if you are just writing single-threaded programs and multiple programs are executing on the same computer, your operating system is actually controlling which core is executing which program. So even if you're only writing single-threaded programs and you have multiple of them running, they might be running on different cores that you can't see. And all you can see as a programmer for single-threaded program is one core and one memory. And you don't have to worry about sharing with anyone else because that's all handled by the operating system. Most applications use one thread. You have been taught to write single-threaded applications. But if you want to start writing multi-threaded applications, you'll have to start worrying about sharing memory because that's something that operating system doesn't manage. You'll have to manage them. So now you are given the ability to use different cores to execute the same program. And you will need to worry about sharing memory between cores. Because multiple threads could modify the same variable without you knowing. Let's see what happens from the programmer's point of view, of course. So this memory is what is present for the programmer. This is the virtual memory that you'll be seeing. Starting from 0, it's the instructions, the global variables, the heap variables that grows down, and the stack that grows up. This is for a single-threaded program. The program counter points to wherever you're executing in the instructions, right? 243. The stack pointer points to the end of the stack here, and it grows up or down depending on your freeing, your function calling, and everything else. When you add a thread to your program, what will happen is you will have two program counters, both pointing to different places in the instructions. Instructions is shared in memory. You'll have two stack pointers pointing to different stacks. So something will manage your memory such that you'll be seeing two different stacks. The stacks will not talk to each other because they're local to your current core, but all of the other ones, the instructions, the global variables, the heap variables are shared. So local variables are still local, so you can modify them freely. Thread 1 and thread 2. Yeah. This is just a summary. Each thread has its own program counter. It can execute a different function. And it's almost always executing a different instruction from other threads, but you can't be sure because they happen parallelly and nothing is controlling that. Each thread has its own stack, so it has its own copy of local variables. Each thread sees the same global variables, so when you're writing or reading the global variables, you'll have to be careful. They also see the same dynamically allocated memory. If you're accessing your memory through pointers, all of those are treated the same as the global variables. They're shared by all threads. And that's why these things can be used for your communications between threads. Threads can communicate through memory. Through global variables, dynamically allocated memory through pointers, and that's a really fast communication because you won't have to do like networking stuff like sending packets and handshakes or anything like that. You just have to modify the communicated global variable. But you just need to be careful the threads don't conflict in reads or write to the same memory. If both of them are trying to write to the same memory, you'll have to know which one happens first. But if they're multi-threaded, you can't really know which one happens first. So, but reads usually doesn't matter. Usually the thing that causes the most problem is write. So, you can also have more threads than CPUs. Time will share across the CPUs, and that's handled by your operating system and your computer's microarchitecture that you'll be learning if you take those courses later. So if you have more threads than the CPUs, you might see actually a performance drop because they're fighting over the same amount of physical resources that you have on your machine. So you have two ways to implement multi-threading. The program always starts in the main thread, so that's one thread. If you need more, there are two options. The first one is using the OpenMP directive, compiler directive. This is really simple to use and it adds the least amount of overhead. Because you can just, when you're doing a for loop, you can just use one line and you can comment it or comment out or uncomment it to disable or enable multi-threading. So it's really simple. You don't have to add anything else. Pragma OMP parallel for will parallelize this for loop that directly follows it. And something that gives you more control is the C++11 threads library. And with this, you will have to do manual creation of thread. You will have to know which function you are multi-threading, and you'll have to know where your threads should be joining. So for this, it will just do it for you. It will multi-thread this for loop and it will join after this for loop finishes back into one thread. And this you'll have to just know how you're doing this. And with the join, when one thread finishes first, it will just stop and wait for other threads to finish and then go on with one thread only. We'll be focusing on the first option because it's simple. Let's say we have this for loop. We're going from 0 to 100, minus 1, and we're adding some two array components into the third array. And we just add this pragma OMP parallel for. What this do is it will create, if we have a 4-core system, it will just detect it and create 4 threads for 4-core system. And then it will just divide 100 into 25, 25, 25, 25 into continuous ranges because continuous ranges is usually faster than you're doing 0, 1, 2, 3, 4, 5, 6, 7. That's just generally not good. Continuous ranges is faster because of how the microarchitecture works. Yeah.
Question. When it comes to like parallel programming, how much of like a benefit do you see? Like for example, in milestone 1, there were lots of pre-computations that we did. I'm how much I'm assuming part of the reason why we're learning about that now, or this now, is because something like parallel programming wouldn't offer as much of a benefit for some of the computations we were doing back in milestone 1.
That's actually a good question. I'll be going to that just right after this. So yeah, let's just continue on finishing this slide. Yep.
Let's say in the code we're adding like if you were adding C to like you're filling an array with like the value of C, right?
Yeah.
And then we're adding previous array values to the new array value.
So you're saying you're writing into C and that depends on previous C values.
Like say you're like doing different options. Is that needs to go?
So if dependencies comes in, like for this, it doesn't depend on anything in the other threads, right? It's just A and B, the same index. And if you need to add independency like Fibonacci, that makes more sense to be serial than parallel, then you have to live with serial.
Go.
Parallel won't work. You'll have to wait for the previous ones to finish anyways. Yeah.
Just thinking about that question, if you wanted, would it be possible to make a workaround where let's say you design or you write it in such a way that it holds in like a place of stasis until a value is defined, and then when that value is defined, then it would carry like the next thread will carry out the operation. It's kind of redundant because like you're just this one of the threads is waiting
Yeah.
for a value to exist and then it will do it, but could you do it that way if
Yes.
you were helping?
It's really common in multi-threading. And this actually is the only way if you want to solve some of the problems. Let's do this simple demo first, and then we'll eventually get to all of your questions later. So this demo, while we're waiting for the ENC to start. So this demo actually answers your first question. What is the benefit of parallel speedup versus your problem size? Let's hope it comes up. Yep. It's the vector one. Should be the vector one. Yeah, vector one. Okay, let's read openmpvec.cpp. So what this does is it defines first the vector length of 1000, and it does some random initialization on the A and B. And then it does some random calculations that are A and B and stored into C. And these are just made so random that it's really hard for the compiler to optimize out. And we record this amount of time. Let's first start with vector length of 1000 and the multi-threading disabled, and let's measure this time. Okay. Let's do make clean first. One thread and it happened really fast. Now let's uncomment this We're adding multi-threading now. So we're using now 16 threads, but we're having about 100 times more time than before. And this is because the problem size is actually smaller than the overhead added by adding multi-threading. Because creating threads actually takes time. And it uses 16 threads. Let's see how many cores are on this machine. LSCPU. So we see this is a 64-bit architecture. It has 16 CPUs. Cores per socket is 8. So you have 8 cores, 2 threads per core. So physical cores, you have 8 cores, and you can have maximum of 2 threads running parallelly on each core. And that means you have a 16 CPU. So you can have maximum of 16 threads. And that's why it gave you 16 threads. Okay. Let's try again without multi-threading. Let's try with a much larger number. See what's the number they gave me. Add 4 zeros. Then let's enable multi-threading. You see a speed up there, right? And how much of a speed up was that? That's about 8. And let's add 1 more zero. And disable this. You see more? Right, we're seeing the same amount of speed up. And that's where we're saturating our multi-threading speed up. So this is the experiment that the teaching team did before. So the numbers are slightly different, but the amount of speed up are still the same. If we use a small problem size of 1000, we see a slowdown adding in the multi-threading, and that's because of the overhead adding multi-threading. It just have to happen when the problem size is big enough that your multi-threading overhead starts become not so important. So we reach the 7.6 times speed up. Yeah.
I have a question. Okay. Let's say you had a problem, like in this example, and you were trying to optimize the speed, but you don't know ahead of time like the vector length can be set in at runtime. But you wanted to enable this to work like to be as fast as possible. Are there ways, depending on like maybe the complexity, that you can use to predict ahead of time which one of these will be roughly faster? And then you can, based off of the output of whether or not the vector that's set meets a certain threshold, you can switch between whether you serialize it or parallel.
Usually, if you want to switch between whether you parallelize it, using OMP is not going to work in most of the time because it's a compiler derivative, right? If you use threads, then you might be able to do it during runtime. Usually, we just collect some statistics and see if this number usually is really large. Because if it most of the time it's not that large, you might not even need multi-threading at all. Okay, convert any program into using multi-threads. We can just, before each for loop, we can just add pragma OMP parallel for. And now, A and B are shared across all threads, even if they are local variables inside main. But because they're declared before the pragma OMP parallel for, they are all shared. They're still treated as the global variables. Local variables inside the for loop, declared inside for loop, are then separate per thread. These are on the separate stacks owned by each of the threads. And now we're just defining A and B. We're adding A and B into A, and we're outputting them. Let's think about what will the program output be. Any idea? Let's pause and do a typing speed contest. And after this, you'll have some idea. So we only have 2 people here, so it's perfect. You two will do a typing speed contest. I will ask you two to come up, and one of you will use my laptop. One of you is going to use this keyboard. And on this window, one of you is going to type on 1, the other one is going to type on 2, line 2. And the type, okay, it's not showing now. The thing to type is this. Let me see how can I group that. All right, I think. Yes. Yes. Type this line. I am an amazing electrical and computer engineering student because I am a great typist and program is mostly about typing speed wins. One of you is going to type on line 1, one of you is going to type on line 2. And whoever wins will get a little present from me. Okay. Let's try it.
Yeah.
Yeah. And you can discuss which one was one.
Yeah, I'll do one.
Wait till I say start.
Okay.
You're
Are
ready?
we gonna type? I'm on one.
Okay, okay, I'll be on two.
That's it.
Huh?
You can go to.
Wait, what?
Yeah, I'm on two now. No, I'm
Wait, what?
And you're not allowed to do backspace after I say start.
Okay, okay.
okay.
Yeah.
Wait, but are you one?
You
Wait.
have to switch by the arrows because you have to fight over
I'm
typing, right?
and
Okay.
You have
I
to fight over the cursor.
Okay, okay.
Okay. Not allowed to use backspace. Ready? 3, 2, 1, go.
Oh my God. Wait, what?
Just
Okay. Wait, I'm already lost. Oh.
how I'm going to play it.
Okay.
Okay. You see, neither of them is actually making sense.
yeah.
Both line 1 and 2. And that's actually the point. So both of you will get one present. And pick which one you want.
Thank you.
And it's the last day, so okay. So from what you just did, you see that it's actually you have two parallel cores. You have two different keyboards. You have one keyboard to yourself, so you can be doing parallel programming. But you're fighting the only one cursor that exists on your screen. And that's what the programs are doing when my slide is not working. What's this? Open again. So what you just did was just mimicking what the printf multi-threading is doing, because printf prints to the shared one single print buffer. Here. Hit the wrong thing. Okay, here. So for this print for loop here, we have different threads and they're all fighting over the same print buffer. Everyone wants to be writing its own thing. So your print is going to mess up. The only thing you can do so that your print doesn't mess up is for you to communicate. You say, I want to finish my line first before you can actually print. So you're asking someone to wait for you until you finish your current line and they can do the next line. Yep.
But in that case, doesn't that that kind of seems like at that point it's not worth doing.
Yes, it's actually not taking advantage of full parallel work. And that's actually something that you might consider not making parallel. But if you want to still make it parallel, this is the way to fix it. Let's think we don't need this anymore.
Outputting betas. Or if it's.
This is for any shared resource that you're fighting over. And printing, outputting is actually the easiest one to see. Yep.
Is that why like there's a limit on how many cores you can use as well? Because as you increase them, like the same issue of like they're now fighting for more and more space beyond a certain number of cores.
That's one of the reasons. The reason why you can only use this many cores is actually a combined reason, really complex. So usually for researchers, they'll just experiment and pick the one that usually is the best. And you can't just pick the best one because there is no best one in all scenarios. So now, this is the same code. I'm enabling both parallel force. And let's make clean first. We see the output is messed up, just like what we just did. And we're seeing something that's really not making any sense. Okay. The thing we can do now is we can uncomment this line. Pragma OMP critical. This defines what is called a critical section. And this refers to the line right after this, or the block right after this. If you want to make multiple lines critical, you'll just have to add a block like this. Here and here. The critical will make the next line or the next block critical section. I'll just do the line. And critical section means you'll have to wait. Once one thread is in this critical sections, all other threads will wait until this thread finishes it, and then the next thread can enter. Let's try it. We see all outputs are making sense now, but the orders are still messed up because it's parallelized. So parallel will just unorder everything, and that you can't help. This is the syntax. Inside a parallel for, you can add a pragma OMP critical to define critical sections. Only one thread at a time can execute this block. It's just like a traffic control. But making everything critical will just destroy your performance, making a serial again, and that defeats the purpose of making this block parallel. So if you're doing just one output for this for loop, there's no reason of making this parallel because it just doesn't make any sense. Okay. Let's get back to our milestone 4. Fast path finding. algorithm choice, and parallelization. These are just some times that are recorded by the teaching team using the n equals 175, d equals 20 test cases on 370 interesting intersections. So 317 depots. If we just use iterative A star, single threaded will take 1,280 seconds. And we treat that as the base case. Then we compare parallel iterative A star. So we don't do anything other than making it parallel. So we're parallelizing the k squared v log v. And we get a 7.6x speed up with parallelism. And we're constrained to 7.6x because we only have 8 physical cores on our system. We can do 16 threads, but because some of the resources are shared across each two threads on each core, so it's really constrained by the number of cores rather than number of threads. So 7.6x is the most we can get on these computers. Multi-target Dijkstra itself gives 33x speed up just by using a better algorithm. So that's a lot more speed up than just adding parallelism. Then adding parallelism on top of this brings us to 250x speed up. Algorithm plus parallelism. So the best practice is always to tune your algorithms before trying parallelization. So parallelization is the last step if you want the last bit of speed up. And it's usually constrained by a constant. Let's see how can we parallelize our milestone 3 code. So we have a priority queue. We have our vectors, nodes, and key intersections. For each of the key intersections, we treat them as the source and we run multi-target Dijkstra. This is the for loop that we want to parallelize. And inside the for loop, we are calling the multi-destination Dijkstra find paths that uses all of these global variables. Okay, is this code making sense? This is the multi-target Dijkstra function, and we're calling that function for each of our key intersections as sources. And we want to parallelize this for loop. And that will just have each thread executing a different version of this function. Like this. Will this work? Given our global variables, will this work?
Will there be any issue with like the front?
Yeah, because you are modifying the wavefront as if it's just to yourself. But if your global variables are shared across threads, you're going to mess up. So you want to keep your variables that you are doing private to itself. So you will need to privatize your global variables like this. Now, what about the last variable, key intersections? Will that affect anything?
I'm not sure, but I think so, because isn't it the case that, you're going through all of the intersections in key intersection, and you're doing multi-target diagram for that in specific intersection, and so when you parallelize it, it's just going to split how those key intersections are, like, it's gonna split them up
Yeah,
into different threads and that.
so they're not interacting with each other and they are not written too. You're just reading. So it's okay. If you just read, not write. Yeah, if you have to write it and the other threads are reading the same thing, they will get confused because they don't know like whether it's the right one that it reads. So yeah, it's okay to keep that there, and then let's consider these ones. How about if we define the wavefront nodes key intersections inside here as local variables? Will this work? And then we pass them into the find path function by reference. Will that work? Remember, they're local variables that they're before the pragma OMP parallel form. Are they private or shared? They're shared. So even if they are local variables, they're still shared. So it still doesn't work. Local variables declared before the parallel 4 are shared. So it won't work. So the best way to write it is just this. Inside each of the find paths, it has its own wavefront and nodes. Okay? And let's go to the demo. I'll be using the golden solution. We'll make. Flow. Because I did make clean. Let's look at the portion of the code that we're going to be looking at. It's in find all paths multi-threading, and it's this OMP parallel 4. Initially, we will be running the same thing with parallelization enabled, and then we'll disable parallelization and let's see what happens to the runtime. Okay. We'll just run ECE297 exercise 4, run tester. We'll do easy Toronto. See the numbers. So traveling courier took 0.76757 seconds. Test time 0.77 seconds. And I guess this is the one that we want to remember. And now I'll remove this OMP parallel 4. I'll compile in here so it doesn't mess up the terminal. Make file, change it to release all. And launch target doesn't matter, so. This should be faster because we're not make cleaning. Remember, it's 0.77 before. .02. So it's about 0.8 times speed up. Less than 8 times. Less than 8 times because it's constrained to less than 7.6x, and there is also the traveling courier that takes time, so it's less than 8 times. Okay, next part. We can break our parallelization. So currently it passes, both of them passes. I just re-enable parallelization and I will go here. And I will be first showing you what will happen if this nodes vector is kept global. Let's see what will happen. Let's still do the same thing. If we have parallelization enabled, crashed. Halted with sig abort, likely causes memory corruption. Assert failure. Could not parse tests. So it's a memory corruption of somehow. And it's going to be really hard to debug because it just tells you memory corruption and it doesn't tell you where, it doesn't tell you what happened. Okay. And another possibility is if we left the priority queue global. Let's try this. You already know it's going to fail. Oh, it's actually the same thing. So something like this will just get random errors. These ones, they get the same error, memory corruption. Sometimes it just seg faults. Sometimes it will give you a wrong answer. We can keep trying until it gives a wrong answer, but I don't think that's worth it. So the failure conditions will be really randomized. Post this one.
What's the program?
What's the program we're running on? You mean what am I running I'm testing the easy roundel test. It's this one. It just runs the traveling courier once.
Did you parallelize the?
Yeah, it's parallelized and I just kept the priority queue global and will. Okay, I think this is meaningful now because it's clearly stuck. This is one of the random outcomes that rarely comes up. So we won't be waiting for it to time out. Okay. When you get some random failing conditions with parallelization off, the first thing you want to do is you want to turn off your parallelization and see if it passes. And that usually quickly narrows down the problem. Let's see. Passed. So I just turned off parallelization and I had the same code as before. It passed. And so that is a sign that something's wrong with parallelization. Then the next thing we want to do to debug it is I will go to a tester. I will run debug tester to download the test file. And then I will go back. I will re-enable our parallelization. I will change this to unit test debug so I can run the debugger. And I'll change the launch target to test lib street map. Really slow. Okay. I'll run the debugger. I think it's because the launch target is doing some weird thing. I'll build again with this specific build target. And I'll choose this one. Okay. And let's see what happens now. So this time it actually crashed. And let's see where it's crashed. Let's go to the call stack. Expand this so it's easier. Okay. So if I just collapse everything, you'll see we have 16 test lib street maps because we're parallelizing. And I'll go to the one that pauses on exception. And I will go find the function that I'm familiar with that I wrote. It's this one. Find multiple paths from intersection. And we see we're pushing into traversal Q, and traversal Q is, we go to the definition of traversal Q is this priority queue. And that's a sign that we have to put this priority queue into our private space. And in this case, you can just stop here. And let me see. Okay, so yeah, and that's why I usually think crashing is the best case in a lot of, yeah, because if you crash in the debugger, you will quickly find out where you crashed and you can find the last responsible line and you'll quickly have an idea of what's going on. If it stucks, that's the worst case, especially in the debugger. And what you can do in the debugger is, as long as you find it stuck, just click on pause and go into each of the threads and see if multiple threads are trying to write to the same thing. Usually they'll be trying to resizing the same things and write to it, and probably the processor will get confused and it will just hang there. But in the most cases, it will just crash. And then the worst case is when it finishes without any errors, but it gives a wrong answer. That's the worst case because you won't even know where to look at. You just have to wait for one crash. So for these kind of things, the most effective step to do is always disable parallelization. If it solves the problem, then something's wrong with parallelization. Probably you're trying to access some global memory that has to be made private. If something's not able to be made private, another thing you can do is to add the critical section line so that you ask that this data can only be modified by one thread at a time. But that's the last resort. Most of the times, just making them private just solves most 99% of the problems. All right. Get to the So that's that. Recall estimating the travel times and saving them into a 2D array or matrix. We can store the matrix into a vector of paths like this. And the first vector is the sources, the second vector is the destinations, and each of these stores a path from source to destination. And you can customize a path type to store the path itself. And you can just define the paths here. You can parallelize this for loop to find the paths from source to destination. But is it okay to push back to paths here? What will happen if we do this?
Oh, wait, path is a global variable, so, won't it be that when we parallelize it, according to the rules, try to write into path?
Yeah. If you do pushback, And pushback always pushes to the back of the path. But if multiple threads are trying to push back at the same time, then where will this pushback happen, right? Because path is public and there's no way to do pushback at the same time. And you cannot just make path private because it has to be public. Because different threads have to write to it to store your final result. So no, this won't work. So what we can do is we resize path first to the number of sources, and then we can store with the index so that we're not interfering with each other because each thread will have its own unique index. So we're just writing to its own place. And that's usually a common source of error. I have debugged this a few times in past years. So when you're trying to write something that has to be shared, just make sure you're writing to a dedicated place that you know won't be touched by anyone else. Okay. Yeah. A summary for debugging parallel programs. The first step, the most important step, disable parallelization. If the problem disappears, then there's probably a race condition. Multiple threads are writing or reading a shared variable. Then open debugger. Examine the call stack for where it gets stuck, for where it crashes, for where it's likely a race condition when multiple threads are writing to a same position. And then we fix the race conditions either by privatizing the variables, by making them into local variables, or we can use the OMP critical to force that only one thread can do this at once. This is not as good a solution because we're sort of removing parallelization, we're sort of adding in serialization to something. So only use this when there is no other way. And this is something that could be really helpful. Amdahl's law. This is the formula that people use to estimate how many speed up you can get by parallelization. So suppose we have n cores. F is the fraction of parallelizable work. You cannot just parallelize the entire program, right? You can just parallelize part of it. So F is the fraction of the part of the program you're parallelizing. And the speed up is one maximum speed up, not the actual speed up, maximum speed up you can get. It's 1 over 1 minus F plus F over N. So usually if we want to analyze whether this parallelization works, we can just set n to infinity. If we set n to infinity, then this one is 0. So the speed up, maximum speed up we can get is actually 1 over 1 minus f. Yeah.
How do you estimate like the fraction of parallelizable? Like how do you get that fraction? You look at higher.
Usually when you're actually developing in industry or something, you probably, when you are writing your code, you will have a profiler running always. So the profiler will be recording the amount of time you spend in each of the critical sections of your program. And you can usually have an idea of how many time is spent in each of the steps. So if you want to parallelize one step, you will have an estimation of F.
But doesn't how long you spend in like each critical section depend on like how fast that section is? Or am I misunderstanding? So
So
like,
this F is the F in terms of serialized, like single-threaded program.
Oh,
Yeah. This F is single-threaded, and if you want to parallelize at the proportion F into multiple cores, you don't know how many cores you're going to parallelize it in. This is the function, this is the equation to use. And you can use this speed up calculation to see whether your parallelization is actually worth it or not. Okay, takeaways. Improve your algorithm first before doing parallelization because that will give you the most gain. Add OpenMP pragmas because it's really simple to implement and you can disable them at any time. There's no cost of disabling one line versus disabling like creation of threads, creation of callback functions, creation of, I don't know, forks, joins, and everything else. Avoid modifying shared state, minimizes bugs. If there are problems, privatize variables so each thread has its own copy. Parallelize large chunks of work instead of parallelizing everything. So only parallelize the work that are worth it to be parallelized. Multi-threading is hard. Even experts will get it wrong. So it's open research questions, usually. So all of the formulas we share in this presentation are actually sources of analyzing whether using this is practical or actually beneficial in a lot of ways. So don't panic, M4 is hard. Even if getting a really basic version working is fine. Like we're not asking for a lot, but there is a competition. So if you really want to aim for the competition, you'll have to spend a lot of time looking at it, researching. So, and for suggestions, always get something simple working first. Working is usually the thing that gets you passing in the course. If you want to aim for higher and higher, build it on top of what you have already working or simple. And parallelizing should be the last step of your work if you want a further challenge. Okay. And that's it for today's presentation. Any questions? If there's no questions, I'll just end this recording.